Welcome to today's class. So in this class, we are going to be looking at the physics practical for what JUPEB. This year, what we are asked to do based on the information we have, based on the instruction paper, we're expecting a setup like this, what we have here, just like the one we have in the drawing too. So now what happened here is that one thing that makes it a bit different is that you were expected to give you a stopwatch, which means the possible thing we have inside here is 2 experiments. So I'm going to be rounding them up as one. Though in some of the exams you find out that they will show you those instruction in the instruction paper, they will come and do different thing altogether. They might choose one of it. But notwithstanding, we are going to be looking at the whole thing generally, combining it together as a unit, working on them at the same time. So the first thing we're likely to see there, based on this setup, is like we're likely to look for Hooke's law, experiment that has to do with Hooke's law or the simple harmonic motion. So we're going to be doing it together here, combining it, and then I'm going to be plotting the whole graph. But now what's happening is that we're not going to run this experiment, how long it can take. I'm going to show you one shortcut method. We're going to use some methods to do it faster and easier. Now, I'm going to take up the masses given to us is 10, 20, 30, 40, 50, 60, and 70. Now, the mass hanger is not, the weight of the mass hanger is not given. Perhaps in the exam, you may be given the actual mass hanger. But for for our class purpose, I'm using 20-gram mass hanger in this. And the ones I'm going to do is just 2 of them. The rest of them, I'll show you how to use calculation to get the rest of the information that you need in plotting your graph. From there, we'll move into the plotting of the graph. Direct, we'll move into there and do it immediately. So now I'm using mass hanger of this. The first thing, if you look at this now, if you look at the Hooke's law aspect of it, to do that, we're going to measure, check we have a pointer. We have a pointer, our meter rule, the split cock that's holding it. Now, what I'm going to do here is first to check the initial length of this spinal spring before I continue. So now, let's see how we go about that. So this one, what we have here is 27. From here, we have 27.5. So 27.5. So what we are going to do now is to add our mass in it. So if we add our mass in it, so I'm using, like I said, I'm going to be doing with 50 grams. Then I take the simple harmonic motion of it too. This is now 2020. 2020, we need 10 grams to complete it. Or should I just use 50 direct? Let me just use 60 direct, 50 direct. Okay, because we're talking about 50-gram hanger, I just 20-gram hanger, that's what I'm using. If I add 20, if I add 20 to it, it's 40, then I add another 10 to it, then we have 50. That means the mass I'm using now from the instruction is that I'm using the 30 grams, additional 30 grams to the 20-gram hanger, making it worth 50. So then I will hang it. We have a 27.5 there, cm. Then I hang this one on it. So what do we have? Then let's see. Excuse me. Okay, easy. Yeah, no shake. So what we have here is we have what we have here from that 20, 57 from 57 down to 7.5. We have one. We have 1.3, 1.1, 1.2, 1.2. We have 1.2, 1.2 cm. Alternatively, I think I should take the actual distance. We have it to be one from there. In this place, we have 58.7. 58.7. So 58.7, 57.5 minus 58.7 minus 57.5. We have a 1 point. We have what? 1.2. 1.2. So we'll take the oscillation now. We're going to be taking the oscillation of this. So let's see what we get. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The 20 oscillation for this is we have a 7 point. We have 7 points. For the 50 oscillation, we have a 7.06 seconds. Let's repeat. 7.06 seconds. Then repeating it again, we have this thing. What is wrong with my time? Listen, what is wrong now? This is refusing. I used to. Oh my god. Okay, let's try again. This thing is not picking up. It's like the button is bad. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, what we have now is 7.31 seconds. So we're done with this. The next one I'm going to do here is let's take up 50. So if we're doing let's take on 80. That 80 means that I'm going to add how many here? 60 grams you need to get 80. If I add 60 grams, this is a 20. This is another 20 grams. This is another 20 grams, making it what? 60. Now it's 60. So these are the only ones that we're going to do. Then the rest will be the other way around. Now let's check what we have here. So we have Well, we have 59.2. 59.2. If it's 59.2, 59.2 minus 57.5. We have, what we have there is, we have 1.7 cm. So let's do the oscillation to know what you get. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So our first one is, we have 9.303 seconds. So let's repeat again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The next one we have 9.29 seconds. So for our 50, and this is all we have to do now. So the rest we are going to do now is, I'm going to show you how to use formula to get the rest of them, so that you have a smooth graph. So in this one, the rest of the, let me use perhaps 70 grams. Remember, we have for Hooke's law. So for the force here now, we have 70. I'm using 70. 70 will be converted to what? Kilogram. If you convert to kilogram, we have equal to 0.07 kilogram. So now multiply by 10, we'll convert it to force. The force now will be times 10, that will give us 0.7. Give us 0.7. 0.7 now. Force constant I got in this one is 3.33. That is Newton meter. Then it's always nice to, when we get whatever we have, we convert it to cm, so that it will be easier for us to do the calculation, the graph. It will be easier for the graph to be done. So we have this to be our force. Have it to be our force. What is wrong? Oh. Force is 0.7 Newton. 0.7 Newton. So our force is 0.7 Newton. So with this force, what do we do? You use this formula. We have our force is 0.7 Newton equal to constant, our spin constant, times E. So when we cross over, we have E to be extension to be 0.7 over 3.3. So what do we get? 0.7 divided by 3.3. So we have for this 70, we have 70 grams. We have what? 0.021. This is a meter. Then to convert it to cm, that will be times what? 100. To multiply by 100 times 100, we'll have, what we have here will be what? 2.1 cm. That is what you get here. So just with this method, you get the other one. Now let's quickly go to the other one, how to calculate the oscillation, the period of the oscillation. to get this one done, what we're going to do now? What we're going to do, let me save time. So to get the period, we can use this formula for the period. This one has not started giving me problem again. For the period, we can use this formula 2 pi over k. So with this now, we can get the rest done. So now let's look at this mass must be also in kilogram. Remember, about 70 is what is it this? No, it's not this. Is where's my, it's not this one. So our should be 0.07 kilogram. That is our mass. So our constant is what 3.33 Newton meter. So what do we do next? To get this, we're going to do period is equal to 2 pi. We have our 0.07 all over 333. So when we divide this, let's divide and see 0.07 divided by 33.33. You have your, this is in standard form. (0.07) divided by 33.33. What we have is what? 2.1 times 10 raised to the power minus 3 all squared, then pi, our pi, and then when we square the square of this, we have 0.045, let's stop here, 8 times pi, which is 22 over 7 times what? 2. So if we are doing this, what we have here will be times 22 times 2 divided by 7. We have what we have, the first of this for the 70 will be equal to 0.288 what? Seconds. So with this, just with this, you're going to be able to get the rest of the work done. So now what we'll do now, I'm going to move over to the table. I'll show you the table, then we'll go into the plotting of the graph. That's the major area I want us to pay attention to. So with this now, note this thing very well, like I told you, watch it very well, watch it, and then see how I got this one. So with this now, we'll be able to do the rest of them. Now, if you watch out this, it will help you to save time. It will help you to save time in your work so that you will not. So now this is what the table look like, and the two places that have asterisk is where the ones I did. No, that's the ones I did. And remember, we were able to calculate the periods theoretically. Now I want to show you something. That's why I left this place open. I want to show you how you can get the other value of this. Remember, you have to take the mean, the average, or the average of these two. Now if you look at here, you have to take the average. So now remember the period. How did we get the period? For this period we got here, we use that formula. Let me still remind you the formula that says that period is equal to 2 pi square root of mass over what? Constant. First constant, the one for my this thing is what? Para spring is 33.3 Newton meter. That is what we use. So with this now, for that for that 40, if you can still remember, where we have 40 grams, 40 grams should be converted to, this 40 grams should be converted to what? Kilogram. We have 40 grams. Let me just refresh your mind a bit. And we have 40 grams, that is 40 grams divided by 1000. We have 0.04 kilogram. That is what we have. So with this thing now, what next? We can now substitute it for this. We have for the mass now, the mass we have 0.04 all over 33.3 times 2 pi, and then equal to what? T. So what's the next thing to do now? When we divide, we can do the calculation. We have 0.04 divided by 33.33. What we have here is 1.2 times 10 raised to the power minus 3 all squared 2 pi equal to t. So our pi, as we know, when we square this, square root of, when we get the square root of that, the square root of the value, we have 0.034. Maybe we'll leave it at what? 6. We'll leave it at 6 there. Times pi is always 22/7 times 2. So 2 now times 22 times 2 divide by 7. So what we have as our period now will be equal to 0.217. We can say approximate. We can approximate it towards to maybe 8. So let's see what we have here. Okay, here we have a 7. There is no approximating that side. Okay, but let's continue with this one I have here. So now, to get this value, what we do here is that you just remove maybe a number here. We can remove 2 here. 2 from this, we have 4.34. If we minus 2 from here, now what we have will be, we will get 4.32. You can also remove something like 1, so that there will be a little variation. So now when we add it up, 4.34 plus 4.32 divided by 2. So we have, what we have here will be 4.33. That's what we have, 4.33. You can see that 4.33. This 4.33 now, what we do, we can now divide it by 20. We divide by 20 to get the period for 20 oscillation. See that we arrive at the same thing. This is what we have. So approximately 217. So that is how we arrive at this. So now the next thing we're going to, the basic thing we want to go into now is how to plot the graph. Look at our values. If you look at our values, you find out that, and we're going to be plotting a graph of mass against period, that is mass will be in the vertical column. It will be in the vertical while the period will be in the horizontal. And also we're going to be plotting a graph of mass. Mass should be in the vertical, and also this other one, the extension, should be in the horizontal. So let's go ahead. When we look at this, I hope I will not take too much time on this. I don't want to waste much time. This graph plotting. So when we look at this now, we're going to be using this graph. This is a 1 cm graph. So what it simply means is that by 1 cm graph is that from this point to this point is 1 cm. We will count from this small one, from this side I'm pointing now, we have 1. So we have it from here. Let's say this one now. We'll have 1. This is from here now. I have 1, 2, 3, 4, 5. That means that is to say 2, 4, 6, 8, 10. That means for each line from here now, from here, this of the line is 2 cm, 2 millimeter, not cm. This is 2 millimeter. From there to 4 millimeter, 6 millimeter, 8 millimeter, and what? 1 cm. 1 cm. 10 millimeter make 1 centimeter. So now we want to look at how to get our graph done. In most cases, the graph should be at least it will be at least it should take 3/4 of your this thing of the graph paper. 3/4 of the graph paper. That is what you're going to be using. So in this case, when we look at this, you find out that this is said that the mass will be where? Mass will be in the vertical, and then the period square. I want to use this value here. That's why I said it there. So this is what we're going to be using against this, and then this other one. I guess let's first do this one, the mass. That is the one that has to do with Hooke's law. So if we do this, we choose your scale. It's best to choose a scale of a multiple of 2. Multiple of 2 or multiple of 5. It's always easy. So when we look at this one, so we started from 40 then to 90. So what are we going to do? If you look at this place, you have this place from this is 2 cm now. 2 cm. We can say, okay, let's think about this. So let's consider here 1. This can be our 10. This can be our 10. 20. This can be our 10 now. This is our 0. If this is our 0, we have our 10, 20, 30, 40, 50, 60, 70, 80, 90. So that's what we have here. So we can say 2, 4, 6, 8, 10. 6, 8, 10. That means 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, let's go by that. 2, 4, 6, 8, 90. We have 10 here. That is 100 grams. This is 100 grams. This is our 0. So let's see what we get the other side. Now where we have 1, we started from 1. So but then what do we have? We can say This is another 2 cm. This is 1, 2, 3. We only the whole thing stop at what? 2. The highest number we have here is 2.7. So what are we going to do? 2.7 cm. So what are we going to do? Let's see if we can use. Let's see if we can use a how many cm now? We have 1, 2, 3, 4 for 1 cm, 1 unit. Then this our 1 unit will be here. This is 1. This other one will be another 1, 2. It's not, I don't like using small scales. It means that we still have some space. Let's see if we can extend it a little. So we have this is okay. Let's leave it here. We have 1 and what? 2. It looks so small to me. It's too small for me. 2, and then we can say 1, 2, 3. Let's go with it. Okay, this one is what? 1. This one is what? 2. And this one is what? Oh, 2. This is what? 3. This is 3. This one is 3. This is 2. This one is 2. So, like I said, here is 10, 20, we have 20. This is 30, we have what? 40 here. This is 50, we have what? 60 here. This is 70, we have what? 80 here. This is 90, we have what? 100. Okay, everything is okay now. You can see our alignment. Then to be 100. So what next are we doing now? So we're going to be we'll draw our line. Okay, we have our line. Then we put our quantities. This is mass in grams. You remember the units. This one is what? Period squared in what? Seconds what? Squared. The next thing we do here is to plot it. So when it's 20, when we have 40, what do we have here? 1.2. This is 40. We have 1.2. So from here, since we have here to be 5, what does it mean here? What it means is that from here to this place, we can say, let's count it and see. We have 1, 2, 3, 4, 5. That means each of these, when you jump one of it, you have 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, and 5 millimeter. Now, but then we have our unit said, our values here say 1.2. That means what we have here is what? 1 millimeter, and then 2 millimeter means 1.2 here. So we take it a bit up. When we go up, we have here to be 1. We have here to be 1. We have here to be 1. No, I think I made a mistake here. This has to do with cm. This has not period yet. I'm not solving that period. This is what? Extension in what? Cm. So that's what we are solving for now. So here is what we have: 1 cm, that is 1 millimeter. 2 millimeter, we'll stop here. Then that means it's giving us 1.2 cm. Okay, the next one we have 50. 50 is 1.7. So this place is 50. 1.7. So he said here is 2, 3, 4, 5, 6, 7. This was 7. I'll put our line again. So the next one we have is what? We have the next one, 60. That means 1.8. This is 60. This is 60. This is 60. Here is what? 7. Then we have 80 somewhere here. Maybe let's check it. This is 1. This is 1. 1 millimeter, 2, 3, 4, 5, 6, 7, 8. This is 8. We stop here. This is our 8. So the next one we're going to be doing is the next one is 70. When is 70? 70 is here. 70 is here. We have 2.1. This is 2. And then we'll stop at 70.1 is this one. So the next one we have is 80. 80 is, this is 80. This is 2. 2.3. 1, 2, 3. So we have it here. So the next one we have is what? 90. 90 we have is what? Where? In 90 we have 2.7. This is 90. This place is 90. We got, which is, this is 2. 90. This is 90. We have it 1. This should be 5. So it's 2 point what? 2.7. 1, 6, 7 somewhere here. So we are done with this. So we can join the whole thing together. So this is our graph. That's how it looks like. So in this our graph now, we can also find the slope. Actually, I'm taking so much time in this. So to find the slope, you can take this point. So for our slope now, we have this one. I'm taking okay. That place is 90. We have change in what over change in what e. So we have this place is equal to what? That's 90. Subtract from what? This is 40 all over this place should be around, let me see, this is 1 cm, 1.21, 1. Okay, this is 1.2, that's the lowest. We have it to be what? 1.2. Subtracting, here we have, this should be what? 2. This is 5, this is 6, 7, that is 2.7 cm. So when we do this, when we subtract, this will give us 50. When this subtract, we have, this will give us 5, this will give us 1. So let's see what we get there. 50 divided by 1.5. We have, wow, 3.133. That is will be this one is grams, gram cm. So that is our slope. That's our slope. So the next thing we're going to do, let's do the other one. This thing is taking too much time. In this second one, we're going to be plotting time, this period square over what? Period square against what? Mass. That is period square will be in the vertical, while the mass will be in the horizontal. But because of the time, I will just plot it and show you how it look like, so that will not be I do not plan to take this too much time in this graph. I will just get it done and show you the graph itself. So this is what the last graph looked like. This is what it looked like, and if you look at it, we find out that the two ones vary so much. The variation they were a bit away from there, but the other ones that we use that formula, they tend to be aligned very, very well. So this is where I'm going to be stopping. We're going to end the class today. And if you're joining for the first time, I want to encourage you to subscribe and like. If you have any question, you can also leave it in the comment section. Thank you.